This evening's speaker, Ronald Hoffmann, is the Frank Rhodes Professor of Humane Letters at Cornell University. He was born in what was then southeast Poland just prior to World War II. Given the course of his professional life, it is interesting to note that his father was an engineer and his mother was a school teacher. In 1941, he and his family were sent to a ghetto, and then shortly thereafter to a concentration camp. He and his mother were smuggled out of the camp by his father in early 1943, and they were successfully hidden in the attic of a local nearby schoolhouse by a Ukrainian citizen for the remainder of the war. His father was killed by the Nazis later that year when they discovered that he was planning yet another breakout. After several relocations in Europe following the war, he arrived in the U.S. on Washington's birthday in 1949 with his mother and his stepfather, Paul Hoffman. He quickly learned his sixth language, English, and went on to graduate from the highly selective Stuyvesant High School of Science in New York City. He enrolled in 1955 as a pre-med major at Columbia University, which meant that science was a major component of his undergraduate program. Summer internships at the National Bureau of Standards and at Brookhaven National Lab whet his appetite for scientific research and began to shape the course of his career. As we will find out later this evening, he developed a passion for other endeavors while at Columbia. He has recounted that the world that opened up to me before me in my non-science courses is what I remember best from my Columbia days. I almost switched to art history. Well, to the great good fortune of chemistry, he didn't, and he began his graduate work in theoretical chemistry at Harvard in 1958. Following brief stints at Uppsala University in Sweden and at Moscow University, where he participated in a US-USSR graduate student exchange, he returned to Harvard, where he joined William Lipscomb's fledgling research group. While at Harvard, he and fellow graduate student L.L. Noor developed a model for understanding the bonding in molecules that ultimately became known as the extended Huckel theory method, and applied it to the bonding in boron hydrides and more generally to polyhedral molecules. He also got hooked on organic chemistry and began a long colleagueship with Robert B. Woodward, who had a profound influence on his career. Following the award of his doctorate and a 3-year postdoctoral appointment at Harvard, Professor Hoffman joined the chemistry faculty at Cornell University in 1965. A quick calculation reveals that he is now in his 41st year at Cornell. He identifies the major professional contribution in his long and illustrious career as that of a teacher, a role in which he takes great pride. He has taught primarily undergraduates while at Cornell, and almost every year since 1966, he has taught first-year general chemistry, chemistry courses for non-majors, and graduate courses in bonding theory and quantum mechanics. Beyond the confines of Ithaca, he has shared his knowledge and understanding of applied chemistry, applied theoretical chemistry, very broadly in the chemical community at large. You should know, in fact, that we had to make sure that his visit to our campus this evening did not conflict with his teaching schedule. In fact, after the talk tonight, he's going to get back in his car and drive back to Cornell because he has classes tomorrow. He has, of course, been recognized by his peers on many occasions. These honors include the 1973 Arthur C. Cope Award in Organic Chemistry, the highest recognition conferred by the American Chemical Society in organic chemistry, and that award was conferred jointly with Bob Woodward. The 1983 award in inorganic chemistry, the highest recognition by the American Chemical Society in inorganic chemistry, and he is the only person to receive the highest awards in 2 different subfields in chemistry from the American Chemical Society. He received the 1986 National Academy of Science Award in Chemical Sciences, and just to show that all his recognition is not in chemistry, he received the 1988 Pergamon Press Fellowship in Literature Award at the Jurasi Foundation in Woodside, California, where he was in residence for 3 years. In 1990, he received the Priestley Medal, awarded by the American Chemical Society for distinguished service to chemistry, and of course, he was a co-recipient in 1981 of the Nobel Prize in Chemistry, which he shared with Kenichi Fukui for his work in analyzing the mechanics of chemical reactions. Over the years, he has published over 500 research papers in chemistry, but perhaps more surprising is the fact that his love for poetry and literature has resulted in the publication of several collections of poetry, including the Metamix, State, Gaps and Verges, Memory Effects, and Soliton. Old Wine, New Flasks, Reflections on Science and Jewish Tradition, co-authored with Shira Schmidt, is a book exploring the intertwined voices of science and religion. He has also authored 2 popular science books, Chemistry Imagined, Reflections in Science, and The Same and Not the Same, as well as a play, Oxygen, co-authored with a fellow chemist, Carl Jurasi, that premiered in 2001. When Dean Prezant first told me that Professor Hoffman was going to give the Sokol lecture this evening, I actually became very excited. I know, those of you who know me know I don't get excited very much, but I actually got excited. Finally, I was going to have an opportunity to have explained to me some of the questions I was left after reading The Conservation of Orbital Symmetry, which was co-authored by Robert Woodward and Ronald Hoffmann in the late 1960s. However, not to worry, Professor Hoffman has chosen to speak on chemistry's essential tension, the same and not the same, rather than the conservation of orbital symmetry this evening. The only option I think left to me at this point is to get Professor Hoffman to actually autograph my book this evening. So, please join me in welcoming Professor Ronald Hoffmann.
Thank you very much for the lovely introduction. Actually, we share a mentor that with a very special relationship that I have with him in the field of solid state inorganic chemistry. So let's talk about chemistry. If you asked a few hundred years ago, what is chemistry? You'd get us an answer that chemistry is the art, craft, and business, before it was a science, of substances and their transformations. And this went on before there were chemists, because people were transforming matter for their own benefit, for profit, for altruistic reasons, for thousands of years. Just make a point here. Here is an Egyptian wall painting from Luxor from Thebes, a mere 3,500 years old. The blue and the green in this, and the blue in the gate of Ishtar from Babylon. It's a blue enamel baked onto bricks. This stood in Babylon, and then by a feat of imperialism for a change not American but German, found its way to Berlin. Or if you look at the blue behind the green in this remarkable Hellenistic wall painting, period of realistic art predating the European Renaissance by a long shot. That blue is not a natural product. There was a blue all the time, used as a pigment. It was ultramarine, lapis lazuli, very expensive powdered lapis. But this is not. This is a product of human transformation, of photochemistry, product of Egyptian, this is Egyptian blue, a pigment made from, related to the glass and enamel discoveries of the Egyptians, essentially a glass frit with the usual components of a glass to which some copper mineral was added, and it's the copper that gives it the blue color in this particular instance. The same blue, now here you see some of the Egyptian paintings that are behind this technology. If you go to Luxor, try to get the guides to take you away from the tombs of the kings and queens into those of the viziers, because it's the viziers who depict more everyday life in their imagery on their tombs. And here you see very clearly, let's try this laser point, it's not very bright, but you see here people who are placing a crucible over a fire, others are treading on bellows. These are processes in the refinement of gold going on in the middle of that process. The blue that is in the Chinese figures here of not quite as old perhaps, but is also a variant on the Egyptian blue, or the Chinese blue, also copper-based mineral. Anyway, the point that I want to make is that people were making these things, and it's not just pigments, it is also medicines, cosmetics, metallurgy, food preparation, all of these things people were transforming matter before there were chemists. Now in order to, I would like to show you that because it is so fundamental in chemistry and still remains a part of chemistry. But in order to do that, I would need to do a demonstration, and I somehow didn't think that the safety committee of this hall would let me explode something. So I will, the chemistry is going on in our bodies is both so slow and so fast that it does not serve well as a demonstration. Enzymes churning things over 1 million times a minute, and there are other processes which are fortunately a little bit slower. So instead of bringing a demonstration, I have to show you some slides. So here are two substances. A reddish-brown liquid with a gas above it, that's bromine. Next to it is aluminum. These substances were not available in pure form a few hundred years ago. In fact, they're a product of the last 2 centuries. Aluminum, for instance, on the right, Napoleon III served his best guests on the dinner plate made from aluminum because it was more precious than gold. And the tip of the Washington Monument, for the same reasons when the monument was built, was of aluminum and not gold. But only 5 years after the monument was completed, a young man in Oberlin and another young man in France, both 23 years old, found a process for making that aluminum so cheaply so that no one would ever think of putting it on top of the Washington Monument anymore. Anyway, one substance is placed into the other. You get flames, smoke, foul odors, absolutely everything you expected of chemistry. And you get a fundamental transformation. At the end is a complicated aluminum bromide that looks nothing like the aluminum, like the bromine that started, and which has very different properties. Okay, this is chemistry. This always was chemistry, including the flames and the foul odors and the smoke. These things, along with beautiful colors and nice crystals, are what still attracts young people to chemistry. If you want to hear a good story of this by someone outside of our profession, take a look at Oliver Sacks' recent memoir, Uncle Tungsten Memories of a Chemical Boyhood, for a description of the attraction of what this basic transformation, which is going to be a theme of what I will say, in ways that you'll see, has on young people. Now there are some consequences of this situation, and here is one of them. This is a 1942 Walt Disney comic book. Some of you of a certain age will remember those things. those days, Karl Barks, one of the original members of the Walt Disney stable, he actually drew the whole comic book and wrote the story. That would never happen today. It would take at least 100 people to do that, and lots of computer power. And you see here, I don't know how much we'll see of this story here. You can look a little bit. If you can't read it, doesn't matter. The usual things happen. Donald Duck comes in, the nephews are playing with something, he does something stupid. There is an explosion, there's the obligatory egg on the head. You notice nobody's wearing safety glasses. My chemist friends are saying there is never any chemistry in the popular literature, so what if benzene is misspelled? Not chemistry there. Actually, the most interesting thing here is this, the next panel, which I've blown up. You can read it yourself. If I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen. The nephews respond accordingly. The interesting thing, just for the chemists in the audience, is that to this day, this experiment has not been done. And a good next exam, you can ask the question, why is it is difficult to mix CH2 with NH4 neutral. Okay, so that was fun, but it was also in it something else, something about the perception of chemistry by the general public, and that is that chemists are the people who make things go bang. Okay, that's part of the image of chemistry, and we will come back to that. Now let me mention another interaction of this first definition of chemistry in terms of fundamental transformation with a culture in a very different setting. This is now a Greek manuscript, and you see here Ouroboros, the snake biting its tail, a symbol. Here is some other illustrations. When there arose in a number of cultures, in India, in China, in Egypt, in Greece, in Europe in general, philosophies of transformation, hermetic, secretive. What kind of transformation? Of course, desired transformation. Of a sick person into a healthy one. Of a mortal into an immortal, a vain hope. Of a base metal into a precious metal. When there arose these philosophies of transformation, which in some way were counter-religious and ran into trouble with the religious systems wherever they arose because they dealt with the work of the gods or the God in the hands of men. And yet they were attractive, these philosophies of transformation, because they partook of some basic human myths of transformation, which in turn powered in their own way a number of the religious systems. This is the myth of the Persephone returning from the dead, the myth of Phoenix rising from the ashes, the myth of the resurrection, or of resurrections in general, or of reincarnation. When there arose these philosophies, and they were abstruse, and they needed something with which to get into people's minds with, like a logo, a slogan, they chose to use that thing which, before there was chemistry, nevertheless represented transformation, and that was chemistry, even though before there was a name for it. So they chose chemistry, and then those philosophies were co-opted by chemistry. They began to do experiments, and those were fun of themselves, and sometimes they were useful. And so you get a picture. What I'm talking about, of course, is alchemy. Here's a typical alchemical illustration. Alchemy lends itself, because of its pictorial connections, and there's an interesting connection here to chemical structures and the pictorial aspect of chemistry. 40% of the page of my papers are illustrations, pictures. Here is a typical late alchemical illustration. In the back is a bishop marrying a king and a queen, and in the front people are doing chemical experiments. Now, in the 1960s, I went to lots of hippie weddings in California, and I never saw anyone doing any chemical experiments, except of a certain kind. What's going on here is obviously something on a symbolic plane. The union that's taking place in the back is symbolic of the union that's taking place in the front, or maybe it's the other way around. Okay, so there's something about transformation here that's very interesting. This is not your usual take on alchemy. The usual scientist's take on alchemy is that of a pseudoscience, but to put it another way, is that alchemy, what modern chemists would like to do is they'd like to keep all the chemistry that alchemists provided, because they did do good chemistry. They made for us the mineral acids in the Middle Ages in Europe for the first time in quantity, the nitric, sulfuric, and hydrochloric acid. And you can see that the vessels here, though they also are related to the vessels of the crafts and of metallurgy, that the vessels survive to this day in our science. So what chemists would like to do normally is to take the chemistry that the alchemists did, to forget about the philosophy, and to chuckle a little bit nervously about the charlatanry that inevitably accompanied something like the transformation of lead into gold. But I don't think that's right. I think alchemy is something very different. Alchemy is a very interesting and unique and cross-cultural experiment in which a philosophy and chemistry got together. And that's very unusual. And there are a couple other things to say about this. One is not original to me. It comes from Mircea Eliade, a historian of religion, who said the following. He said, "Modern chemists, crying to high heaven that they have nothing to do with alchemy, have accomplished exactly what the alchemists set out to do, which is to turn dirt into gold." Dirt is what Bristol-Myers Squibb uses as the starting products for its syntheses, and the gold is what we pay for the products. Okay? So and now there's another side to it. As you see from these images over here, something about alchemy captured the artist's imagination, and not just the artist. There is something about this transformation that's very basic. And so here is the situation. We have modern science, which has accomplished this much, which has somehow lost the imaginative mystique of alchemy. We need it desperately. We need a perception of science, of chemistry in particular, which captures the imagination as much as the alchemists did. We don't have it. Let me show you this. This is a late alchemical painting. So this is commissioned by a late Medici Duke. I slipped my mind which one it is. He's the guy who's seemingly making the omelet at Wright. And in 1570, he dedicated his chemical laboratory. And so the painting is dated here. He hired Jan van der Straat. This painting hangs in the Palazzo Vecchio in Firenze, if you're there. Hired Johannes Stratensis, it's here, to do this painting on occasion of this dedication, and it's many things. It's a court painting. So here is the donor, and that wonderful androgynous figure in the middle is Bianca Capello, who was then his mistress and later his second wife, a very interesting person in her own right. And around there are the accoutrements of the chemical laboratory. Now, the reason I show this to you is in part because this is the first illustration I know in art of the sociology of scientific research. So let me explain. You see this guy here in a coat and spectacles, which were pretty expensive in 1570. He's the master alchemist. You notice that he is gesturing in such a way that it's clear that he is not doing anything, but he's telling other people what to do. That's the professor. Okay? And all those other people around here, those are the students. There's even one up there that's cut off who's making lab notes in this. Okay, it's fun, this painting, but another reason I want to show you is we think science is more important in our society. But here is the Duke, a Medici Duke, who is choosing on the occasion of dedicating this laboratory, his laboratory, choosing to have himself painted as a chemist, as an alchemist, doing an experiment. I would like President Cole, the time when she dedicates her building next year, is that right? Let's see if she can do the same. It's hard to imagine President Bush or Pope Benedict ever doing anything like this. So, is science more important in our time? Not so obvious. Okay, that's the end of my first of three tours that I'll take you through chemistry. And this is following up the definition that chemistry is the art, craft, and business of substances and their transformations. Okay, in the last 200 years, we have learned to look inside the innards of the beast. What I mean by that is that with hard work, cool and hot work of our mind and hands combined, and without waiting for any microscopes to show us what is there, we, using our fallible senses and our tools, have learned that inside these substances undergoing transformations, on a microscopic level, there are atoms, and much more interesting than atoms, that there are persistent groupings of atoms called molecules, so that now there is another parallel definition of chemistry, and that is that chemistry is the art, craft, business, and now science of molecules and their transformations. And every chemist today carries those two definitions in their mind and mixes them up hopelessly so that you talk about substances but you show pictures of molecules, or you talk about molecules and you transform substances, and it's been an extremely creative activity. So here are some of these molecules, just to show you. Of course, these are models of molecules. So you see here 4 carbons in the shape of a tetrahedron, and 4 hydrogens radiating out, tetrahedrane, cubane, dodecahedrane, the platonic solids here displayed in the molecular form. These are models of molecules that are very small, 10 orders of magnitude down from the size of my hand. And finally, you see at last, on the right, a molecule that should be on the flag of Brazil, the molecule shaped like a soccer ball, Buckminster Fuller. These are molecules. Are they typical? Well, we'll see in a moment. They are clearly, I think, beautiful. They are simply beautiful and beautifully simple. And they're devilishly hard to make. And just something for the young people in the audience, I'll just say something and you can think about the consequences of what I said. Of these molecules, the last one chronologically to have been made by human beings, it may have been made in nature before then, the last one to have been chronologically made is the soccer ball shaped molecule, which was for the first time thought of or detected in reality, was thought of a little earlier, a mere 21 years ago, and made in quantity only 16 years ago. And that molecule, the last one to be made, is today by far the easiest to make of these 4. I'd like you to think about what that means. Okay, now, the moment I show you these molecules, I feel guilty. And let me explain, it's my problem, not yours. But let me explain why I feel guilty. The reason is just what I said, that they are simply beautiful. And I'm going to show you a molecule that's not simply beautiful, but to me is the most beautiful molecule in the world. It's this. This is the last time someone built an actual physical model of a protein with all 9,500 or so atoms in it, about 4,500 hydrogens, about 2,500 carbons, 700, give or take 100 nitrogens and oxygens, also 12 sulfurs and 4 irons. And it looks like a holy mess. And here is a little simplified. So many of the atoms have been removed and just the inner coils of the backbone of this biopolymer have been shown. So what is this tapeworm quadrille? A bunch of pasta congealed from primordial soup. Not quite evolved. This molecule is that biochemical molecule which we know about more than any other biochemical molecule. It has 1 or 2 chapters in any biochemistry textbook devoted to it. It is, I cannot keep it any longer from you, the oxygen carrier in our blood, and that's hemoglobin. And on the scale of simplicity, complexity, it is light years away from tetrahedrine and cubane. And I had to learn to love it. Once I learned, I loved it. But I had to be taken by the hand by a good teacher and by coercion to learn to love that molecule. And I reflect on that, and what is really behind that has little to do with chemistry, but it has to do something with human psychology and how we function. And that is basically that hemoglobin molecule is complicated, and these molecules are simple. So where is chemistry? Well, chemistry is in both of those. It's also a lot of molecules in between, but on the scale of simplicity, complexity, probably closer to hemoglobin than it is to tetrahedrine, but somewhere in between in terms of complexity. And now I want to reflect on simplicity and complexity. If there is anything simple in this mind, in this world, it's the human mind. Of course the human mind is complex, but what I mean by that is the human mind, for good psychobiological reasons, falls for simplicity every time. There are good and bad aspects of this. There are probably reasons for this. The number of sensory inputs that we have are immense, so that they would be paralyzing if action were not taken on a basis of some abstract, some brief extract of those sensory impacts. When there's a tiger charging on you, you don't have time to cognitively think about the tiger in nature and so on. So that there are reasons for simplifying the information. Now, it's easy for all of us to see the bad sides of this. Here's one, for instance, political ads. Okay, so what are political ads about? Political ads are the best, the highest degree, the highest concentration of visual arts, poetry, and psychology that money can buy for the purpose of convincing you, me and you, that of that particular candidate's simplistic view of the world coincides or strikes some resonance in our mind with our own simplistic view, desperate tracking for simplicity in our minds. That kind of simplistic view is behind stereotyping people, behind racial prejudice, behind all kinds of things. And now, go to science. You think that scientists are smarter. They really aren't, of course. And scientists fall for simplicity every chance that you give them. This is what's behind the wild pronouncements of physicists that this equation must be true because it's simple. Behind the falling of chemists for simple mechanisms. If I've made a living out of this. If this can go in one step, it's much better than if it goes in 17 steps. And it's behind our liking this molecule here, or not having to be told that this molecule is beautiful, and to having to be taught to love this molecule. So that's my minor tirade against complexity. I'll repair the thing in a moment. But it's something about the world of molecules here. We don't want to lose touch of that. One thing you see is, of course, in all of these things, at least in the models, but also in the reality, in the various representations that we give in science to reality. I've seen this, and there isn't one representation of reality. There are many models. I just showed you 2 models of hemoglobin. I've seen a film, 36 views of an enzyme. It's like Hokusai's 36 views of Fuji. There is an underlying reality, but there are many ways of representing it. Anyway, these things are structural. You can see the structural sense. It's exaggerated by the models a little bit. It has an architectonic sense, and I want to move a little bit from that by thinking that by discussing with you that the struggle between simplicity and complexity that you see worked out it's a struggle for our mind by these molecules. It's our problem. That this struggle works itself out also in anything that human beings do. And in particular, if we stay within the architectonic, and if we move 12 orders of magnitude, this molecule is about 5 times 10 to the minus 8 centimeters on each side. If we move 12 orders of magnitude, we come to the scale of this building. And what we see are interesting things about such things. Here is, for instance, an example of simplicity in an architectural setting. We are now at a high point of Islamic architecture. This is the Taj Mahal in Mughal, India. And Agra, you see the bilateral symmetry that is prevalent in the structure. I could have shown you the Parthenon. I could show you one of Andrea Palladio's villas. These things, tremendous influence on the building of homes throughout Europe and the United States. Elements of simplicity, of classicism. But let's look at something else. Here is we're now in Bavaria. This is the Wieskirche, not too far from Berchtesgaden. You see the structure is symmetrical. That's because human beings built it. Okay? Take a look at the nature around it before we go to the building. Is nature symmetrical? Is what we like about nature that it's symmetrical? Is what we like about a wooden table that the pattern is identical with every part of the table? Nature does what it does, and it's unsymmetrical in every possible way, though there may be some underlying symmetries. But what I really want to do is to go inside that building, and here is a detail. There are some straight pieces in this, as in the windows, but we are now in the Baroque, in the Rococo. If any line can be made curled, it will be. I could have shown you a Mexican colonial church that's the same aesthetic, or you could look at the architecture of the Transparente in Toledo, in the Spanish world. These are the same kinds of things. This is the aesthetic of the complexity. Here is in another place at work. This is a South Indian temple at Madurai. Incredibly complex structure, redone from time to time. Here is a gatehouse of Park Güell in Barcelona, Antonio Gaudi's structure. Again, the aesthetics of complexification at work here. Actually, now it's time to say something to be fair. And this is further up in Park Güell. This is the benches, which were made by Gaudi, and the mosaics by his friend, another architect, Giugio. I'm not sure I pronounced that correctly. And this allows me to make my point. I really have been unfair to symmetry and to order and to simplicity. But there are good reasons for it. I told you the reasons. The mind falls for simplicity. Therefore, we have to work harder to come to terms with complexity. Okay, that's the reason. But now I think the fair statement is this, and I'd like you to think. I mean, here is this is a bench on the outside of a park. It falls off on one side on a wall, and the other side is a courtyard. And you're designing this bench, and you make it regular because there is a place for symmetry, for regularity. But how much less interesting would the decoration of this be if the mosaics were perfectly geometrically regular? And how much more interesting it is, how much more beautiful it is, because the mosaics are as random seeming as they are. So I think the fair statement is this. Yes, the human mind favors simplicity, and we have to work hard to overcome it. But beauty resides at some tense edge, neither in simplicity nor in complexity and chaos. It resides at some tense edge where simplicity and complexity, where order and chaos, where symmetry and asymmetry contend with each other, at some tense middle where this happens. And I think this illustrates it in one point. Okay, now you've forgotten where we were, because I went off in this tirade on simplicity. So we were in this, a second description of molecules as, of chemistry in terms of molecules and their transformations. So we haven't talked about transformations, and actually this is a very exciting time now, because for the last 15, 20 years, we have learned not only about molecules at the macroscopic level, but we've learned about their transformations. And I just want to show you, give you a glimpse of this. And here it is through some slides I've borrowed from some work of a great chemical physicist, Richard Zare. And because he resides in California, he made these slides in the Walt Disney style that you see here. So this is a caricature of what happens in a chemical reaction. There is a molecule, ICl, which is a cousin of Cl2 and I2, two of the halogens. And there are two electrons holding the two atoms together, and in comes a photon beam, some light that is, and then there is a Walt Disney type zap, very closely related to what happens to Donald Duck's head at the moment of impact, and that represents the breaking of the bond under the action of the light, and then the iodine and the chlorine travel apart. Okay, they go off, that seems simple, and they actually study how they go off, and they study this in exquisite detail. And one of the pieces of detail that they study it in is that they actually study the chlorine atoms. For technical reasons, it's easier to study the chlorine atom. And as the chlorine atom goes off, sailing off from the midpoint of this breaking, technically called the center of mass, then it goes off, but then there is an electron around it. That electron is moving around the chlorine. The technical word is orbital angular momentum, but not important. It's moving and can move either in this way or as you see it at the bottom. Now, does it make a difference? What I'm really saying is, can you design an experiment to tell between the two, which is what Zare thought about? Well, to the extent that molecules and chemistry, even though they're microscopic, are classical objects endowed in their motions with the same properties that baseballs have and other things as you throw them around. And you saw that in that picture of the structures of hemoglobin or cubate, that there was that very geometrical structural thing. To the extent that these molecules are that way, yes, if it makes a difference at the macroscopic level, whether this one goes with topspin or the other goes with backspin, then it should be possible to design an experiment to detect that. Now, so is it possible? Anyone who's played ping pong or tennis knows you've got a tenth of a second, if that, from the time the ball hits and you somehow detect it's hit with backspin or topspin, if you can't tell it from your opponent's racket motion, which you put into that equation anyway, you have a tenth of a second to move your racket up or down. Otherwise, if you don't detect that, you're in deep trouble. So yes, it's possible to design classically. It makes a difference. Therefore, it should be possible to design an experiment, and then that they did. And they determined that when you shine the light just enough to break the bond, that the chlorines go off with topspin. Okay. Then they went on to do the experiment, and they changed the color of the light by which they zapped the molecule. They made the light more energetic. And what happened was, at some point, as they made it more energetic, the chlorine decided to go with backspin. And then they made it more energetic, and it just changed again to topspin. As if the racket, the light was acting like the racket in some way. Okay, that metaphor is not too great. It turns out that one has come here into the limits of chemistry considered as a classical enterprise. And this is no surprise, because the absorption of light is inherently, between two levels of a very definite energy, is inherently a quantum mechanical phenomenon. And so there is, on the level of quantum mechanics, whose intuition is not the classical intuition of this world. Think of Schrödinger cats and other things like that. On the level of quantum mechanics, you can explain this experiment, and I'm not going to try to do that, but it is possible to do that, and we can understand. The reason I show this to you is because I wanted to show you the exquisite detail in which we can get information. That's a pretty fine detail of a chemical reaction. I want to show you something else. We can, this is a painting by Giacomo Balla, one of the great Italian futurists. Painting was done about 100 years ago. It's in Buffalo, not too far from us. And the interesting thing is that you can do the strobe spectroscopy, that is in a way being pictured here, to give the feeling of motion. You can do that experiment for a molecule through the work of Ahmed Zewail and others in the last 10 years. But if you think about what's involved, to capture the motion of a dog, or even as Edgerton did of a bullet passing through a balloon, you've all seen these pictures at one time or another. What you need is flashes of light which are illuminating this so as to freeze that motion when you see only certain moments of illumination of that. And if you are trying to catch a molecule, it doesn't look like it, but the molecules of oxygen and nitrogen in this room are moving at about 1,000 meters per second. They don't get very far in this room at this pressure. In fact, they get almost nowhere, but before they hit another molecule. But their speeds are the speed of sound. And in order to catch a molecule that's moving at the speed of sound, 1,000 meters a second, and then it itself is, let's say, breaking apart, to catch that motion on the small scale of a molecule takes strobe spectroscopy, strobe lighting, with flashes of light which last of the order of 1,000,000 billionth of a second, 10 to the minus 15 second, or it's called a femtosecond. And we've been able to do that, so it's a very exciting time overall. Okay, that's the end of my second picture of chemistry. Now I come to the third one. And this is in terms of perceptions of chemistry. Now, I've already, because we don't live by bread alone, and it's important to think about what people think of what we do, I've already actually given you a little bit about perceptions when I showed you the Donald Duck cartoon, and when I, also in the story of alchemy in another way. But let us imagine the following situation. Supposing a congressional committee grants me 10 minutes to tell them what is good about chemistry. They never would. This is just a fantasy. First of all, they only want to hear what's bad. And second, they only want to hear what's bad because one senator wants to say something bad about something else. But let's imagine an ideal world where they want to hear something good about chemistry. Now, I'm not stupid, I'm not a politician, but I know that the budget of the National Institutes of Health goes up every year, and the budget of the National Science Foundation does not go up every year. Therefore, I will pick a health-related problem of some sort, something where chemistry impacts on the congressman's end. Okay? My general philosophy for this. So, now, I don't mean to make fun of this, but here's where I went to a medical colleague and I said, give me a tearjerker where chemistry has worked. And so this came out. It's a slide about survival of children with solid tumors. And I will explain this. It's a rather complicated slide, way beyond the reach of most congressmen. What it is it plots the survival rates on a vertical axis 5 years after diagnosis of children with 8 kinds of tumors, and a time scale on the bottom. A few things about this. First of all, those of us who have had children or who have siblings know that as a first approximation, children are pretty well nigh indestructible. Okay? Turns out, in fact, that accidents are the main killer of children, despite that. But in the developed world, not in Africa, the second killer of children in the United States are tumors. That's not generally known. And the tumors of children are different from the tumors of adults, with the exception of brain tumors. They are tumors of mainly of development gone wrong. And for adults, they're mainly to do with passages through our bodies or with contact of our body with the environment. Not entirely, but okay, so I don't know what rhabdomyosarcoma is. There's a reason I didn't become a doctor. So I don't know what these are, but some of these I know what they are. Doesn't matter. Here are various things that have interesting. 1950, 1960, 75, 95. I'm just a poor chemist, and I was taught that you should plot either logarithmic or equal. I didn't know you could just at random vary. But apparently in medicine you can do that. This is directly from the medical literature. Various techniques. Surgery, that was always there. Radiotherapy, despite Madame Curie and radium, substantial amounts of radioisotopes did not become available until atomic reactors and the bomb effort in World War II. So that's why this turns on right after World War II. And then there's chemotherapy, conventional and intensive. Chemotherapy, as everybody knows, is giving the body a cocktail of chemicals, certainly not one usually, which marginally faster kill tumor cells than they kill normal cells. It's no fun if you've known anyone who's had a chemotherapy. But here is my long introduction. I would lose all the congressmen up to now, even if I tried to say it in an amusing way. And they're not, because with Bill Frist there, and he laughs about doctors out of this. The brief summary of this slide is that until chemotherapy came into being, and I will take full credit of that for the chemists, which isn't true, but I'll take it. Until it came into practice here, nothing worked. And then when chemotherapy came on, survival rates for 6 of the 8 tumors came up to 75 to 90%, where they are today, and the rest are awaiting some developments from perhaps young people in the audience. Anyway, there are some 300,000 lives of children saved by chemotherapy here, and that's my point about what chemistry is good for. Yes, but out of the back doors of the same companies making the chemotherapy ingredients, no, not the same companies, because those companies are actually in public purview, and the worst trouble comes from other companies. But this is not meant to be a slide of any particular pollution. It's just meant to be symbolic of the infinity of ways that we have found of fouling our own nest while improving our life, improving our standard of living, and yet polluting this earth and doing some harm to the environment and to our bodies ourselves. And it leads to this two-faced image of chemistry, symbolized here by a drawing by Hans Erning, a Swiss artist, of Janus, the Roman deity that adorned doors, let's say, in a partitioned house as you pass from one room to another. I actually like, the image, of course, is of harm and of benefit. The two sides of what chemistry has introduced into this world, and definitely a component of the image of chemistry in our times. So now I want to say a few things about that. First of all, I actually like Janus, and I like things that have two sides. To me, a door is a passage. It's not a way out. It's not a way in. It could be both. It's a passage from one place to another. It's something about change, so I actually think it is very, very sense. Okay, what do I have to say about this harm? First of all, there are some colleagues of mine, many, who believe that the press is engaged in a cabal to have the word toxic become part of the word chemical, so you don't have to say. The two words always come together, okay? And so they think there's a conspiracy against chemistry. Well, what I would say about that is that, let's see, a few things. First of all, the press is the press. Good news is no news. Bad news is good news. Nothing has changed in 3,000 years. It's always going to be the same, first. Second, I lived for a year in 1960-61 in a place and a time when the press said nothing bad about the chemistry of their own country. And that was Soviet Russia. And that's the only conditions under which you will get that situation, which some of my colleagues would like. And the press is not out there to educate. It's out there to do other things. Okay,